Hi, my name is Ankel Tinoco, and today's problem is consider an ideal CSTR with two inlet and one outlet. Component A is fed into inlet stream 1 and component B is fed into inlet stream 2. The rate of reaction of species A is as follows. Reaction rate A is equal to K naught times concentration of A to the power 0.5 times concentration B to the power of 1.5, where K naught is equal to 0.41 liters per gram mole seconds. The reactor has the following characteristics. The system is at a constant density of 1.03 grams per centimeters cubed. The volumetric flow rate of stream 1 is equal to 11.8 liters per second. The mass flow rate of the outlet stream is 66.4 kilograms per second. The entering concentration of A is 2.4 gram moles per liter. The entering concentration of B is 4.1 gram moles per liter. The conversion of species A is 0.48, while the conversion of species B is 0.43. What is the required reactor volume in units of liters? So let's start with our diagram. First, we will have a block which will represent our CSTR. The CSTR will have two inlet streams, meaning two arrows, two entering arrows, and one exiting arrow. In the first arrow, we will put our volumetric flow rate, which is given to us, 11.8 liters per second. And under that, we will put concentration of A. Under that, on the second arrow, we will put volumetric flow rate of stream 2, which is unknown as of right now, and concentration B. In our exiting stream, we will put our mass flow rate and concentration of A and B. We can then write the density, our reaction rate formula, our K naught, and our conversion rate. XA is equal to 0.48 and XB equal to 0.43. Our governing equations, the ones we will use. First, we will solve for our volumetric outlet stream, which will be V equals mass flow rate out, which is scripted as an M, divided by density. Then we will rearrange our V1 plus V2 equals V3 so we can solve for V2. We would get V2 is equal to V3 minus V1. Then we use those flow rates, those inlet volumetric flow rates, to solve for molar inlet flow rates. So we would get molar flow rate is equal to volumetric flow rate times the concentration of the species. Then for the outlet molar flow rates. So we would do 1 minus the conversion of that species times the molar flow rate of the entering stream. That will give us our exiting stream molar flow rates for each. Then our concentrations, exit concentrations, which will be molar flow rate of the exiting stream divided by the total volumetric flow rate. Once we have those concentrations, we can plug it in to our rate of reaction. Once we get the rate of reaction, we can solve a mole balance for species A. In species A, we would have Na1 minus Na3 minus volume times rate of reaction A equals 0. Since we are solving for volume, we can rearrange the equation to get V equals Na1 minus Na3 divided by rate of reaction. Now, before we get started, we need to convert our density into kilograms per liter. We will do this by multiplying 1.03 grams over centimeters cubed. We will multiply it by 1 kilogram divided by 1,000 grams multiplied by 1 centimeter cubed divided by 0.001 liters. This will allow us to cancel out all the things we don't want, which will let us get 1.03 kilograms per liter. Now we can start with our volumetric flow rate, our exiting volumetric flow rate. We will divide 66.4 kilograms per second divided by 1.03 kilograms per liter. This gives us an answer of 64.466 liters per second. Now that we have that, we can use our second equation, V2 equals V3 minus V1. So 64.466 minus 11.8 liters per second is equal to 52.666 liters per second. Now that we have that, we can solve for our molar inlet flow rates. So we will do molar flow rate of species A is equal to 11.8 liters per second times 2.4 gram moles per liter, and that will give us a molar flow rate, entering flow rate of 28.32 gram moles per second. Now for species B, it would be 52.666 liters per second times 4.1 gram moles per liter. This will give us an answer of 216.457 gram moles per second. Then we will solve for our molar flow rate of the exiting stream, 3. So for species A, we will do 1 minus 0.48, which is our conversion of species A, times 28.32 gram moles per second. This will give us an answer of 14.7264 gram moles per second. For species B, we will do 1 minus 0.43 times 216.457 gram moles per second. This is equal to 123.3805 gram moles per second. Next, we are able to solve for our concentrations. For exiting concentrations. For concentration A, it will be 14.7264 gram moles per second divided by 64.466 liters per second. And that gives us 0.2284 gram moles per liter. For species B, our concentration will be equal to 123.3805 gram moles per second divided by 64.466 liters per second. And this is equal to 1.9139 gram moles per liter. Now that we have those concentrations, we are able to plug it into our rate of reaction. We will do 0.41 liters over gram moles seconds, which was our K naught, times 0.2284 to the power of 0.5 times 1.9139 to the power of 1.5. Now that we have our response, that will be equal to 0.5188 gram moles per liter seconds. Now that we have our rate of reaction, we can solve for our volume. We will do 28.32 minus 14.7264 gram moles per second divided by 0.5188 gram moles per liter seconds. And that will give us a rounded answer of 26.20 liters. Now, to check if our response is correct, we can redo our mole balance of A, which we can do 26.2 times our rate of reaction, 0.5188, and that gives us an answer of 13.5936, which is also the same as the difference of the inlet flow rate minus the outlet flow rate. Our assumptions are, we are at steady state. This is an isothermal reaction. K naught is constant. We are at constant density, which means we can do V3 equals V1 plus V2. And we are in an ideal well-mixed CFCR, meaning exit concentrations is equal to reactor concentrations.